So, welcome everyone to this One World Series seminar on machine learning. Today is my pleasure to introduce our speaker, Hongru Yang. Hongru is a final year PhD candidate in computer science at UT Austin, advised by Atlas Wang. Currently, he's a visiting student at Princeton University, hosted by Jason D. Lee. Hongru obtained his bachelor's degree in statistics, computer science, and mathematics from the University of Illinois, Urbana-Champaign. So today we welcome Hongru to give his talk, Understanding Transformers via Gradient Flow Dynamics.
Thank you, Mauricio, for the very nice introduction. So I'm Hongru. Welcome to my talk. So today I'm going to talk about understanding transformers via gradient flow dynamics. Yeah, so deep learning has achieved like tremendous success in practice. So from the early days in the 2012, we have like a convolutional neural network beat the ImageNet classification challenge. And then after that, we have AlphaGo beating the best human player in Go. And then after that, we have AlphaFold that can predict the 3D embedding of the protein, protein 3D structure. And nowadays we have ChatGPT, we have which show like tremendous ability in math, language understanding, etc. Yeah, so with the tremendous success of deep learning, it's the evolution of neural networks. So in the early days, we have the simple most neural network architecture that is a multi-layer perceptron. And then we have a convolutional neural network. And after that, we have like this ResNet block structure. And for a recurrent architecture, we have a recurrent neural network. And nowadays, we have a more advanced recurrent architecture like Mamba here. So of course, today's main focus will be the one on the right, that is the transformer architecture, which is basically the backbone of basically every machine learning application models these days. Yeah, so the motivation of my research is that despite the huge empirical success of deep learning, theoretical understanding of why neural networks trained by stochastic gradient descent can work so well is significantly lagging. Now the question is, do we really have to understand? So despite the success of deep learning, we also encounter many issues when we deploy those deep learning model. For example, this picture here shows the hallucination phenomena in large language model. That is, so if you ask the language model what weighs more, 2 pounds of feather or 1 pound of bricks, and it will actually tell you they weigh the same amount. And we all know that that's false. Of course, this particular instance has already been fixed in the latest model of ChatGPT, but this hallucination phenomenon like keeps happening for like other different cases. And another example will be Apple's autonomous car project. So this is back in 2015, Apple launched its electric car project. And early this year, we all know that Apple has ended its car project. And similarly for Tesla, so Elon Musk back in 2018 tells us we are going to have like autonomous car driving from coast to coast. And I still need to get a driver's license last year to drive a car. So yeah, so with so many issues, if we want to fix them, and we need to understand the problem. So for me, my research philosophy is that if we don't know the process, then we can know the result. So a core question is, what functions do those models learn after training, and how do they learn those functions? In practice, neural networks are trained over datasets via stochastic gradient descent. And so to answer this question, we need to have a good understanding of the training dynamics of deep learning. So the methodology of my research is through controlled synthetic experiment. So first, we abstract and identify some important tasks in practice, such as NLP. And then we conduct control experiments and investigate the training dynamics. So for today's talk, I'm going to talk about our recent work on training dynamics of transformers to recognize word co-occurrence via gradient flow analysis. This is joint work with my collaborators from Lawrence Livermore National Lab and Ohio State University. So first, let me talk about data distribution. Uh, so first, we have a set of orthonormal vectors, mu I, that serve as word embeddings. So we have two special signals or words in this dictionary. So that is mu1 and mu2, and we want to detect its co-occurrence. And we also introduce a common token mu3 to every input x. And then the rest of tokens are just like irrelevant words. So then data entry, so all those vectors are in dimension RD, and each input x has L tokens. And we consider a binary classification test. So this y can only take values from plus minus 1. Yeah, so for a single data entry, if both mu1 and mu2 are present with probability of half, and the rest of cases, such as like only mu1 occur or only mu2 occur or none of them occur, happen with a probability of 1/6 each. Yeah, so we have L tokens in each input x, and if the token is not mu1, mu2, or mu3, then the rest of tokens are just like random samples from those irrelevant tokens. So that's mu I from 4 to D. And if a data entry has both mu1 and mu2, then the label is 1, and otherwise it will be -1. So I know this slide is a little bit dense. So the next slide, I actually have a pictorial visualization of the data distribution. So recall that so X, based on our data distribution, it can only have 4 types of data. So that is both mu1 and mu2 occur, it will have a label +1. And if only mu1 or only mu2 or none of them occur, they will have label -1. And they have like the corresponding probability. So I choose the probability in this way just to make sure that there are like 1/2 of the sample that have the positive label and the other half has negative labels. Yeah, and so another point is mu3, the common token, it will appear in every input x. And for the rest of the tokens that I'm not writing, they're just like random tokens that are not irrelevant. Yeah. And also another assumption that I made is that each token will only appear once in this each input x. Okay. Yeah. So for the data distribution, if we ignore the random tokens and the common token, we can find out that the data distribution simplified to a logical AND problem. That is, because we want to detect whether mu1 or mu2 are occurring in an input x. So if they are both occurring, that is, they are both showing 1, then the label should be 1. Otherwise, it will be -1. Therefore, it's like a logical AND problem. And it actually, it is classically known that to be solved by a linear model. That is, if you take the your linear predictor W to be C for some positive constant C times mu1 plus C times mu2, and then you inner product this W with each of your token XL, then you subtract this constant 3/2 times C, and then you will find out that if mu1 and mu2 are both occur in the input X, then this sum will give you 2C. So subtracting by 3/2 times C, it will give you a half C, which is a positive constant. But if only mu1 or only mu2, or actually none of them are occurring, you will get a negative number. So the motivation of my data distribution is the following. So there are actually many natural language processing problems that can be modeled as a logical AND problem. For example, if let's say you have a language model and you want the language model to read some prompt, and then it will answer like, "Is Bob eating a banana?" Okay, so if the prompt is Bob is watching a television while eating a banana, then the answer will be yes, because this prompt has both Bob and banana. On the other hand, if your prompt is like Bob is playing computer games, then the answer will be no. Therefore, to solve this relatively simple task, the language model need to detect the co-occurrence of Bob and banana. Of course, on the other hand, merely just recognizing the co-occurrence is also insufficient, because the model will also incorrectly answer yes to description like there's a banana tree outside of Bob's house. So recognizing co-occurrence of words is important, also insufficient ability language model need to have in order to perform many natural language processing tasks correctly. So in our work, we consider a one-layer transformer architecture. So this part is the softmax attention. So sigma is the softmax function. So this part will output the softmax probability, and will go through WV and W and A to output a single number. That's going to be the our prediction for the label. And so WV, WKQ, and W, and they are in our property dimensions. And A is a vector that's going to. So this part we will output a vector, and then it will inner product with A and to output a single real number. So the loss function we considered in our work is we use the binary cross-entropy loss, and we minimize the empirical loss. Yeah, and we define G to be the negative gradient of the cross-entropy loss. So for training, first for initialization, so this is our transformer architecture here. We randomly initialize everything. So for this vector A, we uniformly chosen each entry IID to be uniform plus minus 1. And then so for this 4 Wien matrices W, WV, WK, WQ, we just use random Gaussian initialization. And we set its variance to be on the order of 1 over square root M1, where M1 is the embedding dimension of those matrices. And we fix this vector A through the training, and we simultaneously train WWV, WK, WQ via gradient flow by minimizing the empirical loss we introduced in the previous slide. Yeah, so there are many previous work analyzing the training dynamics of transformers. However, many of those work rely on certain simplifications like weight reparameterization, like you combine WK and WQ into one single matrix, or linear attention, or you just throw away the softmax function. And special initialization, for example, you use diagonal initialization to initialize your weight, and lazy routine. So our work consider like simultaneously training so all the weights by gradient flow. So before we talk about our main result and proof, let me first introduce some notations. So we let L1 denote the samples with both mu1 and mu2, and I2 and I3 denote sample with only mu1 or only mu2, and I4 denote the samples like none of mu1 or mu2 are present. And we define a very important structure in our transformer. That is, we call them linear MLP. That is, you throw away the softmax probability part, and you only consider the signal goes through WV, W, and A. And we define this part to be the linear MLP of the transformer. And it later turns out that this is a very important substructure we need to consider in order to analyze our data distribution. And finally, so for the output of softmax, we can view them as a probability. So here sigma, recall, is that the softmax function, and its input is a vector because X is a matrix, and XL1 is a L1's token, which is a vector. So the product of those whole thing will be a vector, and after it goes through the softmax function, it will also output a softmax probability vector, and we index through L2, and we get the P sub L1 L2. So for the main results, so this slide is very dense. I'm going to parse that very slowly. Before I introduce the main result, are there any questions about the previous the setup, everything? I'm gonna pause for a bit just to see if there are any questions.
Sorry, could you please explain What's the meaning of L?
Oh, I'm sorry. Explain the meaning of which part?
L, variable
L.
L in the previous node.
Oh, so yeah,
Unchanged.
so this L index the so we have L tokens, right? So each input is like if I can go back to yeah, so each input X it has L token. Yeah, it actually index the like which token you are looking at. Yes.
Thank you.
No problem. If there are no further question, let me talk about the main results. Okay. So the main results is the following. So with probability at least 1 minus delta over the randomness of the initialization, there exists a sufficiently long time such that like the following are happening. The first of all, the training loss will become very small. Second of all, the linear MLP network is going to satisfy the following. So first, it will positively align with mu1 and mu2. And recall that mu1 and mu2 is the tokens we want to detect their co-occurrence. So when the linear MLP network sees mu1, it will output something positive. And when it sees mu2, it will also output something positive. And another part is that when the linear MLP sees mu3, it will actually output a negative value. Yeah, that's why there's a negative sign in front. And for the attention matrix, it satisfies that. So if you compare the score between mu1 and mu2 after training and the score of mu1 and mu2 at their initialization, you will find out that their value increases. And so also similarly for the score between mu2 and mu1. That's when your query is mu1, and when the key is mu2, it will also increase. And on the other hand, the attention matrix are going to negatively align mu3. That when the query tokens is mu1 and mu2, that is, when the query is mu1 and when the key is mu3, and you compared with your value at initialization, it will actually decrease. And similar things for when your query is mu2. So if your query is mu2 and your key is mu3, you compare it with your initialization value, and it actually decreases. And so in the previous slide, I characterized like how those values are changing like during training. So in this slide, I'm going to characterize like how big those changes are. So the first result is that although yes, we can see those scores are changing, but their change is actually very small. So the first result is the attention is actually still close to uniform. So the probability of L1, L2 after training, it will be within some 1 plus like little O of 1 times 1 over L. And on the other hand, the samples can still be correctly classified because our linear MLP network will output the correct value. So for example, if both mu1 and mu2 are appearing in an input X, if you take a sum of G mu1, G mu2, and G mu3, it's actually going to be something positive. On the other hand, if you take the sum of G mu1, G mu3, or G mu2, G mu3, they will actually be negative. Therefore, those samples are correctly classified after the training. Yeah. And if you look at the structure of the transformer after training, you'll see that it actually closely mimics to the linear model that I introduced in the data distribution section. That is, this a linear predictor W equals a positive constant C times mu1 plus C times mu2. This mimics the linear MLP part, the behavior of linear MLP. And this G mu3 will mimic the role of this negative bias. Therefore, after the training, it will classify all the samples correctly. So before I go into next section, I just want to see if there are any question for the results part.
This is ImSim, our image simulator, essentially. So real
Oh, sorry, Kevin, I didn't hear your question very clearly.
I'm not sure if that was an actual question. I think that was just
okay.
someone unmuted.
I see. Okay. Yeah. So let me go to the next slide. So the implication of our results is that although the transformer architecture is complicated, so gradient flow will actually force it to learn a simple solution. That is the linear solution that we introduced in the data distribution section. So there are actually previous work showing that GD can make the neural network learn linear functions in the early phase of training. And then the complexity of the solution increases as the training continues. And this phenomena is called simplicity bias. So our result can be seen as extending the simplicity bias of neural networks to the transformer setting. So now I will talk about like the challenges in our analysis. So naturally, to analyze the gradient flow dynamics, we first just write down the gradient flow updates for those matrices, right? However, if you write down those gradient flow updates, you will figure out that like analyzing those updates are actually very, very hard, because we need to analyze like how those column space and row space of those matrices are changing. That's like extremely challenging. And moreover, like different wave matrices are actually affecting each other. For example, like W is affecting the column space of WV. So therefore, if you want to track the column space and row space of the matrix, it's gonna be like a complete nightmare. So the techniques we try to solve this problem is the following. So the key observation is that, so instead of getting the exact value of those four matrices, if I just want to compute like what is the final result of the output of the transformer is, actually knowing this two quantity is actually sufficient. So because this part will tells you what is the output of the softmax probability, and this part will tells you what is the output of the linear MLP. So therefore, based on this observation, we need to track of like two variables. So that the first one is this WG transpose on WV mu. So WG it's one row of W. It can be seen as a neuron inner product with WV mu. And new transpose WK, WQ mu. So this part is actually one entries in these matrices. Okay. However, this is only keeping track of these two quantities are actually not enough, because if you write down like what is the gradient flow updates for these two quantities, you'll find out that there are variables on the right-hand side that are actually not these two quantities. So therefore, what a natural thing to do is that you write out the gradient flow updates for these two quantities, and you figure out there are variables on the right-hand side that are not these two variables. You're just naturally keeping track of what are those variables are behaving during the gradient flow. So those variables are like the inner product between two neurons. So WG1 inner product with WG2, and the WV embeddings of the signal, that is new transpose WV and WV mu, and WK and WQ embedding of the signal. So if you include those four variables in addition to those two quantities in the gradient flow dynamical system, you will figure out that okay, now you have a gradient flow system that is everything on the right hand side are tracked by the variables on the left hand side. Yeah, so in summary, we don't analyze the gradients of the wave matrices directly, because that is a very hard thing to do. And our workaround to the issue is that we form a complete gradient flow dynamical system, shown here. So before I introduce the training dynamics, there any question on this part? Okay. Yeah, so now let's jump into the training dynamics. So we divide the training dynamics into two phases. So in the first phase, we can show that the linear layer of the transformer, that is the linear MLP, aligns quickly with the two signals, mu1 and mu2. And this happens actually for a very short amount of time. And in the second phase, we show that the softmax changes according to their the linear MLP layer, and the training loss is converging to 0. So for phase 1, our main result is the following. So with probability at least 1 minus delta over the randomness in the initialization, there is a very short period of time, T1, such that the linear MLP layer will output the correct value, that is G mu1, G mu2 will output something positive, and G mu3 will output something that is negative. And we can show that at this point, the training samples are correctly classified. And the next implication is that besides the linear MLP layer, all the rest of variable, especially the softmax attention, you can show that like during this phase 1 period, their changes are very small. They are actually very close to their initialization value. Okay, so a proof outline of this main result is the following. So it turns out that if you at the near the initialization, the gradient of the MLP layer, you can write out it roughly satisfies the following. So you just take the sum over the gradient. So this G, recall is that the gradient of the cross entropy loss times its label Y times this part quantity, that is the norm of the neuron and the inner product of the input X with softmax output and mu. And it actually be shown that at the initialization, the gradient of linear MLP, similar for mu2, is very large and also positive, where the norm of the gradient of all other dynamical variables, especially the softmax attention, are actually very small. Therefore, for a short amount of time, only the linear MLP layer will make big changes, and it will output a positive value for mu1 and mu2. Yeah, so this actually explains like why, like after a phase 1, the linear MLP will output a positive value for mu1 and a positive value for mu2. Okay, so what about mu3? So copy the gradient of the linear MLP from previous layer and plug in mu3, you'll find out that what you can show first is that at the initialization, when t equals 0, so this gradient is actually very close to 0. However, because in previous slide we mentioned that during phase 1, G mu1 and G mu2 are actually increasing. Therefore, so G plus represent the gradient of cross entropy loss for those positive sample. That is, those sample both mu1 and mu2 are present. They will actually decrease. And for those gradient for negative sample, they are actually will increase. So which lead to the G mu3 to going down, because this part is going to be positive. It's always going to be positive actually, because the norm is positive, and mu3 there's no sign in front of mu3. Therefore, this part will also be positive. Therefore, the sign of this gradient is actually only determined by what is the sign of this sum over gi times y. And because the for positive sample, this g decreases, and for negative sample, this g increases. Therefore, the entire thing will become negative. So that's for phase 1. And for phase 2, so we have the following result. So with probability at least 1 minus delta over the randomness in initialization, we have there is this a range of time t1 from t1 to t2, but t2 can be very long, such that for all t in t1 and t2, we have mu1 WV, WV. So this is the WV embedding of the signals. And this embedding between mu1 and mu2, they are increases during phase 2. While the embedding between mu1 and mu3 and mu2 and mu3 are actually decreasing. On the other hand, for the softmax attention, if you calculate the score between mu1 and mu2 and mu2 and mu1, they're actually increasing during phase 2. While the score between mu1 and mu3 and mu2 or mu3, they're actually decreasing. So this finished the part of the proof in our main result that talks about the changes of the softmax attention. So to analyze this phase, of course, the first thing to do, we just like look at the gradient flow updates of those score of those dynamical variable. So if you're staring, so those are actually quite complicated equations. So if you're staring those equations for long enough, you'll realize that. So for this WV embedding, we'll figure out that this part and this part, they're actually independent of I. If this probability is sufficiently close to uniform. Therefore, what we actually need to analyze here is the gradient, is the sum of gradient in this complicated expression. And similarly, this property also holds for the softmax attention score. Although this part has like a more explicit dependence on I, but you can somehow massage the expressions into a case such that it will be very similar to what happened for WV embedding. Okay, so for the next few slides, I'm going to show you like how we analyze those two quantities, especially how can we handle this sum of gradients. Yeah, so in order to handle those sum of gradient terms, we actually need to develop some result, like how large those quantities are. So that's our results on automatic balancing of gradients. So what we can show is that like, during phase 2, so this sum of gradients, it's never gonna be too small. That is because this part is always positive. The gradient of the negative gradient of softmax of binary cross entropy loss is always going to be positive. Therefore, the numerator is always going to be positive. So a problem will happen in our analysis if the denominator, that is this part, is going to be too small, or maybe it's going to be negative. However, we show that this part is actually never going to be too small or going to be negative. So that's our first result. So that was meant to be their ratio is bounded by some order 1 quantity. It's because this term will never get too small compared with the sum of total gradient. And we and you may ask like why this difference of the sum is going to be important quantity is because if you look at that, so I2, I3, I4 are those samples with the negative label. That's I2 are those samples with only mu1, and I3 are samples with only mu2, and I4 are samples with neither mu1 nor mu2. So they have the same sign. And the sign I1 are all the samples only are containing both mu1 and mu2. So this term will appearing in your gradient flow update, and similar for this quantity over here. So once we have handled the like the sum of the gradients, so next thing we need to handle is those WK and WQ embedding, because those two embeddings are also included in our dynamical system. Okay. Yeah. So again, to analyze the how these scores are changing, we also need to know the behavior of the WK embedding and WQ embedding for the signals. And we can actually show that those two quantities stay roughly unchanged during training. And this can actually be verified by our experiment result. That's we just plot out how those embeddings are changing. And as you can see from the plot, they are just basically a flat line, through from the initialization to the end of training. So after we have successfully handled the sum of the gradients and the sum and the WK/WQ embedding, we can actually have the following lemma. That is, we can actually simplify our score, the gradient of the score, to the following expression. So that is the score between mu1 and mu2. They will be roughly on the scale of 1 over square root n times big theta of LT, where LT is the empirical loss times sigma 0 square m plus 1 over L. So this explains why the score between mu1 and mu2 are increasing during stage 2. And similarly, for the score between mu1, mu2, and mu3, that is the gradient is actually negative. Therefore, during phase 2, when your query is mu1, mu2, and the key is mu3, you can actually see that the score is decreasing. So with this expression in hand, we can actually show how much is the changes of those score variables and before and after training. So actually, you can you just need to take an integral, and because another auxiliary result is that those empirical loss actually you can show that it drops very fast. Therefore, after you take the integral, the entire quantity can be bounded by this small quantity over here. Yeah. This is a complicated expression, but the message is they are actually bounded to be something very small. Yeah. So after we analyze the behavior of the softmax attention, we need to analyze how the linear MLP part is changing during phase 2. And so that is our second result on automatic balancing of gradient. That is, you can show that those gradient of the linear MLP, they actually satisfy a certain inequality relationship. That is, they are bounded within some constant. And actually, you can use this inequality to show that the training loss of the network will become will be driven toward 0. Yeah. So finally, we have some experiments. So the first plot over here is just to show that the linear MLP part, it will changes at the very beginning and will be quickly driven towards something very big. And so these two lines, green and orange lines, they're corresponding to mu1 and mu2, and mu3. Recall that the linear MLP will output in a negative value when it's the mu3. And on the other hand, for the score variable, that is those like mu1 and WK, WQ, mu2. So the behavior are exactly like our analysis. And like near initialization, their changes are actually very small. So at this part, they're actually almost flat line. And then after phase 1, it will see a more noticeable changes, and they are actually changing accordingly. For example, this origin line is saying that when your query is mu1 and when your key is mu2, they are actually increasing. Okay, and similar for the rest of the curve. And finally, we can also show that the training loss will be driven down toward 0 very quickly from the initialization. Yeah, so this finished my part of the talk. Thank you very much for your time. Now I welcome any questions. Thank you.